Hello everyone, welcome to our demo on Acheron. I am Subhadeep and I am a postdoc at Boston University. This is a joint work with Zichen and Manos Athanassoulis. So this work is essentially an extension of our work from SIGMOD 2020. So we break this video into two parts. In the first part, I will talk about the importance of deletes in LSM-based storage engines. What are the different challenges in realizing deletes in a timely manner in the storage systems and the core operating principles of our solution based on which we prepared the demo. In the second part, Zichen will walk you through the demonstration framework. So he will show you how the whole infrastructure that we have built works. And more importantly, he will walk you through several interesting demonstration scenarios. So today, we live in an era where we have a lot of data, and this data is being generated at a very fast pace. So modern data systems are really built to ingest a lot of data in a really efficient manner and really fast. So LSM trees, which was a storage-based ingestion-friendly data structure, first proposed by Pat O'Neill et al. In 1996, has really emerged as one of the main out-of-place data structures for these ingestion-friendly data systems. So now we have LSM trees or log structures merged tree-based storage engines that span across several NoSQL key value stores like RocksDB, WiredTiger, Cassandra, LevelDB, and so on. You can even find LSM trees in the storage layer of several relational databases like SQLite, MyRocks, and also time series databases like InfluxDB and WasatDB. So how do LSM trees work? An LSM tree has two components. There is a small component that is in memory, which we refer to as the buffer. But most of the data in an LSM tree are actually storage resident, so on the HDD or SSD. So as data come in, we first write them to the in-memory buffer, and this is a super fast process. And once the buffer is full, we move the data to the storage. So as you can see, on the storage, we can have several levels of data. Each level has two properties. One, the data in every level can be scattered across several files. And two, the data in every level is completely sorted. So this is why we refer to every level as sorted component in this example. Another thing that we should keep in mind is that the level of an LSM tree, as we go down the tree, they have increasingly more capacity. So the level 2, for example, has T times the capacity of level 1, and this T is often referred to as the size ratio of the tree. So what happens when level 1 gets full? When level 1 gets full, we choose one file from level 1 and merge it with the overlapping files from level 2 and write the new data as 3 new files. This process of sort merging data between consecutive levels is referred to as compactions. Once again, in this example, level 2 is out of bounds. So if we have to make sure that the tree is in a correct form, we have to choose one file from level 2, merge it with the overlapping file with level 3, and be done with it. So overall, this is how LSM trees work. But what about deletes in LSM tree? As we mentioned briefly before, LSM tree is an ingestion-friendly data structure. So when we have a delete, we do not really go and search for the target entry in the tree and then update or delete the entry in place. Rather, we insert a special type of data which we refer to as tombstones. A tombstone is a special type of key value entry, and the idea is very simple. A tombstone logically invalidates all entries in the tree that has a matching key. So let us try to understand this with an example. Let's say I want to delete all entries that has a key of 5. And my target entry, as you can see in this example, is in level 4. Now, instead of going over the whole tree, finding the target entry and then deleting it, what LSM trees do is that they simply insert a tombstone against 5. The tombstone logically invalidates the older entries with key 5. But note that the older entries are still in the tree. This is great for inserts because we did not spend the time of searching for the entry and then updating the data block in place. We just did it by inserting a new entry, in this case, the tombstone for 5. However, if we want to make sure that the logically invalidated data are removed from the database on a time-bound manner, this is very difficult. So now, if our query changes to something like this, where we want to persistently, that is physically delete all entries with a key 5 from the database within a threshold of DTH, we are in a big problem. Because for that to happen, the tombstone must propagate through all the levels of the LSM tree and be merged with the target entry, which is in level 4. And this depends on how the compactions happen in LSM tree. In practice, the time to physically persist a logical delete depends on several factors like the file picking policy of during a compaction, that is, which file do we choose to compact, how many levels there are in the tree, what is the size ratio of the tree, and even the ingestion rate of the data in the database, because that is what triggers compaction in LSM trees. And as you can see, these factors are often not controllable by the user or the developer. So LSM trees suffer from this problem of unbounded delete persistence latency in practice. To solve this problem, in our SIGMOD paper from 2020, we introduced FADE, which stands for fast delete. Essentially, FADE is a new family of compaction strategies that uses a new compaction trigger and a set of new file picking policies. So how does FADE work? So let's say we have the same query where we want to delete all data with the key 5 within a given threshold to DTH. And we have this timer that we have to respect. What we do is that we decompose this timer and set smaller thresholds for each of the intermediate levels in an LSM tree. So what happens after we realize the delete? So the moment we insert the tombstone to the first level of LSM tree, we start a timer for the first level denoted by A1. Now, during the natural course of LSM operations, if it happens so that at one point in time, the file that contains the tombstone is chosen for compaction and moved down, then everything is fine. You note that A1 is still smaller than D1, so we did not do anything special. We did not have to. In the natural course of LSM compaction, the tombstone moved to level 2. Now, if it happens so that in level 2, when we start the timer, after some point in time, we see that the timer is greater than the threshold that we set, that is A2 is greater than or equal to D2, then fade comes into the picture. Fade comes into the picture by triggering a compaction. So note that this compaction is not based on the level saturation. It is based on how long a tombstone can live in a particular level. And it triggers the compaction, making sure that the tombstone that is present in level 2 moves down to level 3. Once it moves down to level 3, the same thing happens. If it happens to be the case that the age of the tombstone, that is A3, is greater than or equal to the level threshold, that is D3, fade will once again trigger a compaction, moving the tombstone from level 3 to level 4, and thereby purging the logical delete. So I gave you a very high-level idea about what fade does. Zichen will, in the second part, will show you exactly the operations of fade, and you'll be able to see some very interesting results as well.
Hi, I'm Zichen Zhu, a fourth-year PhD student in Boston University. And now let me walk you through the demonstration part of our paper, Acheron, Persisting Tombstones in LSM engines. The overall structure of Acheron consists of 4 parts: the input panel, the progress bar control panel, the emulation panel, and the performance panel. Users interact with Acheron through the following 4 steps. First, users specify the configuration in the input panel, and then users click the play button in the control panel. After that, Acheron will start emulating the ingestion process using 3 different compaction policies. Next, users can watch the animation of how tombstones propagate via iterative compactions. At the same time, users can compare the metrics presented in the performance panel. Let's first go into the input panel. Users can customize the workload by specifying the number of ingests, the key size, the entry size, and the proportion of deletes. Acheron does not really execute such a workload just using the browser's frontend. Instead, it scales down the number of ingests and the number of deletes proportionally to reduce the memory consumption and CPU computation. In addition to the workload specification, Acheron allows the user to configure main memory parameters, including the bits per key for bloom filters, short as BA, and the buffer size for memtable. In many cases, this number is the same as the file size in LSM trees. Besides, users can also configure the size ratio in LSM tree and the disk parameters, including read and write latency per IO. At last, users can further configure the delete persistent threshold, short as DPT, which specifies the maximum age of a tombstone after it is flushed to the disk. In practice, this number is specified as part of service level agreement. In the default setting, we use the workload that contains 10 million 128-byte entries with 25% of deletes. We construct the LSM tree with 16 megabytes for buffer size and 10 bits per key for bloom filter. We set the size ratio as 2 and DPT for 30 seconds, just for illustration purpose. After all the inputs are fixed, we can now click the play button to initiate the emulation process. After some loading delay, we will see 3 LSM trees are being constructed using 3 different compaction policies, consisting of our recently proposed method state and 2 state-of-the-art compaction policies in overlapping ratio and round robin. We choose these 2 policies because they are widely used in production systems, such as RocksDB and LevelDB. Users can control the progress via these 3 buttons: play, pause, and finish, and even they can drag the progress bar. In our visualization, each rectangle represents a mem table in level 0 and a file in the following levels. The glowing bulb next to a level indicates there is an ongoing compaction starting from this level. The file with red solid border indicates that this file is being picked and compacted to the next level. The files with red dashed border indicate that they are overlapped with the selected file from the upper level in terms of key range. All the files with red border are actually the input for a compaction. After this compaction finishes, there will be some newly generated files marked by green solid border. Within each file, we see sometimes it is divided into 2 parts. The length of the left side area indicates the proportion of tombstones in this file. In other words, a file with pure blue indicates that there are no tombstones in this file. The lightness of the left side area indicates the maximum age of tombstones in this file. When the maximum age becomes expired with respect to user-specified DPT, the left side area becomes completely black without any string. With this visualization, you can see how tombstones age and are persisted via iterative compaction when they are being moved from shallow levels to deeper levels. Tombstones are aging when we observe the color of left side area gradually changes from white to gray and even sometimes become black. Tombstones are persisted when they are discarded in a compaction that outputs to the last level. And that's also the reason we do not see any tombstones in the last level. Besides, we may also observe that in some cases, round robin and mean overlapping ratio may have some files that contain expired tombstones. And that's typically the case. There are purely black left side area in this rectangle. And we will never observe any rectangle with purely black left side area in fade because DPT is applied as a hard time to live constant. In addition to the left side area, we may also observe the difference of the right side area. The lightness of the right side area indicates the overlapping ratio. Darker blue means higher overlapping ratio. That is to say, under mean overlapping ratio policy, whenever a compaction is triggered, it will always pick the file with the lightest blue right side area. The overall LSM tree structure is updated every flush or every compaction. If you want to accelerate the process, you can either drag the progress bar as I mentioned earlier. Alternatively, you can also turn on the stable state only mode. With this mode turning on, you will only see the stable state of LSM tree structure after each flash, and all compaction details will be omitted. When watching the animation process of LSM tree construction, users can also compare the metrics presented in the performance panel. There are 12 metrics we tracked here: the number of issued deletes, the number of existing tombstones, the number of expired tombstones with respect to user-specified DPT value, the maximum age of tombstones, the number of accumulated compactions, the average compaction size, which is quantified by the average input size for each compaction, the average compaction latency, the longest compaction latency, also known as the worst-case compaction latency, the ingestion cost, which is quantified by the estimated accumulated time to digest all the ingestion so far over the number of ingestion. Write amplification, quantified by the number of total written bytes over the number of flashed bytes. Storage space, which refers to the space that used to store the raw data and the bloom filters and fence pointers. Memory footprint only concerns the space for bloom filters and fence pointers. Users can further click Show Plots button to see the visualization of each metric. For example, if we want to inspect the number of expired tombstones, we can look at this figure, and we see that the mean overlapping ratio and the round-robin policy have increasing number of expired tombstones when the ingestion proceeds. But the number of expired tombstones for fate policy, which is the yellow curve, remains at the 0 in this process, which is associated with the fact that I mentioned earlier that we will never observe any file that contains purely black left-side area in fate. Another scenario we consider is to examine the performance impact using different DPT values. We can click this button to switch to this mode. Similar to the orange mode, we emulate 3 LSM tree construction, but now they will use the same compaction policy. The only difference is that they will use different DPT value. For example, by default, the first LSM tree sets DPT as 10 seconds, the second one sets DPT as 30 seconds, and the third one sets DPT as 60 seconds. When playing with this mode, we can investigate the performance impact using different DPT values. And now, after we click the play button and we drag the performance bar, we can compare some metrics presented in the visualization figures. For instance, we can look at the age of oldest tombstones, and we observe that the yellow curve never goes beyond 10 seconds. The green curve will never go beyond 30 seconds. And this is because the fate policy strictly enforce the hard time to live constraint, which limits the maximum age of oldest tombstone that would be not larger than the specified DPT value, because the associated DPT value for the yellow curve is 10 seconds, and the associated DPT value for the green curve is 30 seconds. We will also expect that the blue curve will never go beyond 60 seconds because the associated DPT value for the blue curve is 60 seconds. Users can also compare other metrics like the number of compaction and the write amplification in these figures. Summarizing all above functionalities, Acheron helps users to understand the life cycle of tombstones and how our method fate achieves timely persistent delete compared to state-of-the-art compaction policies. In conclusion, Acheron provides key insight into the impact of out-of-place deletes for LSM-interested practitioners and researchers. With that, I would like to conclude. Thank you so much.